Thanks. Ooh, part of the screen is cut off. Okay, I want to talk about a new perspective on touch input today in the context of user authentication. So here's a demo of our biometric touch sensing system. What we're doing is we're sensing the user's identity every single time they interact with the device. So for example here, when Paul touches the mail icon, his email opens. So what you don't see behind the scenes, Paul is continuously authenticated by the system. Every single time he touches an email or scrolls the screen, the system makes sure it's him. Now the key to implementing this is a prototype device that we built called Bioamp. It senses biometric features of the user's wrist, and then it modulates a signal onto the user's body, which basically travels down the hand, such that the touchscreen device can pick up this signal as part of the very touch event, and then associate the user's identity with the touch event itself. So when John puts on the device, the touch device identifies him and opens his email, so he can interact with his email, and he's continuously authenticated over and over again. Someone else comes in, touches, email shuts down, it's not John anymore. Okay, let's look at the typical process of user authentication in general. Typically, it involves two steps. First, you authenticate, then the session is wide open, you start interacting, start reading emails, interacting with your photos, and so on. And this is really a process that we've been carrying out for a long time. Ever since then, you provide your credentials, you have access to your files. Well, a lot has changed in the meantime. We now have biometric sensors to authenticate users, but this process fundamentally is still the same. And it really begs the question, is this secure now? Can we trust this initial authentication when it comes to interaction with applications? Because if you look at my home screen here, you have access to my messaging apps, you have access to my email, personal, you have business email, you have photos, and like everything that I care about is right here. So if you take my device, you can interact with my friends in my name. So can we trust this initial authentication? Some app developers have decided we can. So Mint, for example, asks you to re-authenticate when you open the app, or 9, which is a popular email app on Android, actually protects your emails with a PIN code. Every time you open your email, you have to provide another PIN code. And then the App Store itself asks you to verify who you are the moment that you buy an application. So if you think about this, this is exactly what we want. You open email, you should authenticate. You send an email, you should authenticate. You delete something, you should authenticate. But it's really, really disruptive to the interaction, so we don't really like it. It's not very convenient. So with biometric touch sensing, we're seamlessly integrating continuous authentication into regular interaction. The current implementation is this. The user identity is part of the session, right? It's somewhere there in the background, and then we have touch events in the form of X and Y. What we're proposing with biometric touch sensing is promoting the user's identity to every single touch event, and importantly, obtaining the user's identity from that very touch event on the screen itself. So as a result, we get continuous authentication during each touch interaction, which is seamless and transparent to the user. So they don't see any password prompts, there's no disruption whatsoever. It looks, in many ways, it looks like interaction with a single user system for them, but it's secure because they're being re-authenticated over and over again. So in terms of the related work, there's a bunch of related work on per-touch user authentication. So let's start with smartboards. If people pick up differently colored pens, then the screen or the device can actually associate input with the user based on the color, because the board can detect which pen was picked up. This ring prototype here uses a connection to the wristband, which modulates a signal onto the ring so that when users use it to touch an item on the touch screen, the screen can actually associate that with the user and then detect who invoked what functionality. The wearable key is very interesting because it's also a wristband, and it modulates the signal onto the user's body instead. So there's a custom electrode on the mouse, which can then sense the signal and associate users with the input events that are being forwarded to the laptop. Diamond touch is very similar because users, when they make contact with the surface, they close a circuit so that the table can associate each input event with a user sitting in one of the chairs around it. And in a previous project that we did called Bootstrapper, we identified people based on their shoes with a camera that's facing downwards. And we're also tracing input events on the surface back to the table edge so that we can associate which user around the table caused that event. So capacitive touch fingerprinting senses the impedance to ground for each user and reliably tells two people apart as they're interacting simultaneously with the device. And finally, in previous projects, both RichPad and Fibero, which we presented here at UIST 2 years ago, we proposed touch input device that can sense fingerprints upon touch on the surface so that we can identify people when they interact with the touch system. So these are great prototypes, but the question is how can we actually integrate this with existing technology, the types of devices that we use on a daily basis right now? It turns out that the answer comes in the form of a wearable device, but this wearable device is very different from the ones that I presented in the related work earlier. It's not a token, but in many ways it's an extension of the touchscreen itself. So it does two things. It's a watch prototype that does biometric sensing, and it transfers the biometric features directly to the touchscreen. So as one possible biometric feature, we're using bioimpedance of the user's wrist as a unique feature. There's a lot of literature on that. If you're interested in that, I encourage you to check out Corey Cornelius' PhD dissertation on that, very detailed. We have 8 electrodes on the inside of the band, a high-precision impedance converter. And what we're doing is we have these electrodes around the arm. I don't know if you attended the TOMA presentation yesterday. It was a beautiful explanation. We're actually sweeping through 12 different frequencies, measuring the impedance between pairs of electrodes, and then model a profile for each user. Here's just an example of 2 different users, and just by plotting the magnitudes, you can see how they're different, and this is unique and stable over time in order to identify them. Details on the paper. We also have a display on the device, and it's really interesting because it turned out that the main feature of, or the main purpose of the display was actually to serve as an anchor, so that when people put on the band, it roughly sits in the same location and the electrodes don't move too much. So next is the data transfer to the touchscreen. Touchscreens measure changes in capacitance when you approach them with the finger, so we need to influence that. But the main challenge here is that Bioamp and the tablet are not connected. They're only connected when you make contact using the body as a conduit. There's the separate ground references, and also a big problem is the filtering on the touchscreen. Touchscreens are designed to filter out all kinds of noise, power lines, and so on to provide really reliable touch recognition. But what we want is the opposite. We want to get a signal across. So essentially what we need to do is we need to jam the system and basically persevere all the filtering. So we're doing that using a flyback transformer at a peak-to-peak voltage of 50 volts. Frequency is 150 kilohertz, which is roughly in the range of frequency that the touchscreen uses to drive the lines. And then we're modulating that onto the user's body through skin using another electrode that sits on the inside. So and that allows us to transmit a signal through the finger and the touchscreen to read that signal upon touch alongside each touch event. Importantly, however, Bioamp does not identify the user. Bioamp merely converts something. It reads something the touchscreen cannot read. It converts it into a feature that the touchscreen can read, and then the touchscreen actually performs the actual user identification. So as a sensing platform, we use an unmodified commodity touchscreen, in our case a Microsoft Surface Pro 2 tablet, implementing the typical projected capacitive sensing, running Windows 8. And we're using something that we've done before, a body print presented at CHI this year. We're looking at the raw signal that we get from the device. Raw in quotes because it's after all the filtering. This is what it looks like. Here I'm touching the screen. We can detect shapes too. And now I'm turning on the modulation. And what you see now is the signal along the same sense line. It's off again. Here's a signal. So if we break this down to a single sense line, this is what it looks if there's no signal applied. You get this spike here for the touch contact where the reading shoots up. And if we modulate a signal, we're basically causing this zigzag pattern, which is very characteristic along the same sense line. And this is what allows us to actually transfer information through the body. The problem with this debug interface is that it's pretty slow. It has a variable frame rate, on average 29 frames per second, and the reliable throughput that we get is 12 bits per second, which is not a lot. And for that reason, we needed to encode something into, we needed to change something about the signal encoding. So because of the low frame rate, we're limited to basic on-off keying. We had to use this as a simplex channel, so we had to make sure that the information absolutely comes across correctly. and all of that as a result of not being able to have full control over the chip. So what we're doing to compensate for this is we have a Bluetooth chip on the device that sends the biometric features to the touch device. Each touch device assigns bioamps within range and ID, and then that ID is modulated onto the user's body such that the touch device can associate that ID with the biometric features, identify the user, and then associate the user's identity with each event. So not optimal, but there's hope. We're actually in conversation with Atmel right now. They seem pretty excited and interested in that. So they have a product, it turns out, the Max Stylus here, which does exactly that. It communicates with the touch chip before all filtering. And we think this is exactly the gateway that we need in order to get higher throughput into our system. So I'm going to condense the biometric identification. In summary, we're using a support vector machine with logistic models, which give us a confidence score, and then we're rejecting all classifications below 95% accuracy. Details in the paper. Okay, then we integrated our approach into the OS. So Windows has a lot of really nice APIs to intercept touches and then analyze what are the processes that are running right now. In the bottom row there, we use the accessibility API to see what's going on the screen, to modify it, to show something, to change elements on the screen, and then the diagnostics in order to inform the process which user has started it, for example, and load the correct profile and so on. And here's what it looks like if you actually implement all that. These are the applications. I can't show all of them, more in the paper. Let's look at input first. Here's a very common one. So an internet browser, if you open it, per se, doesn't need to know who the user is. You can just browse. But over the course of using it, you build up a session, right? You have a history, you have your bookmarks, you have your tabs open. So when Paul comes in, the browser actually knows who it is, opens Paul's session, restores it, and says, oh, you can pick up where you left off. Now someone else comes in, the tablet recognizes that and says, okay, different user, I need to give them a fresh session. Similarly, store. So here Paul opens the store, anyone can browse the store, but the moment you want to buy something, you need to be authenticated. We don't do that through passwords, you just tap buy, which allows you to buy and download an application. Now of course, not only do you have to be authenticated, the system also has to verify that you have enough money in your account. So this is not the case here. Now John comes in, and then the system recognizes, okay, Paul opened the store, but John taps buy. What should happen now? Are you buying this for yourself, John, or are you buying this for Paul? We can also authenticate access during output. So in the case of notifications, for example, we only show the presence of a notification. And then you have to touch and hold it in order to actually read it, similar to Snapchat. So when someone else comes in and touches the screen and says, I got nothing for you. So because we get the raw image, we can also sense particular gestures and enforce them. So for instance, if you have a very confidential message, we can ask the user to shield parts of the screen, and then we show the notification within their hand. And we actually generalize this to whole applications, such as a financial application where we require the user to hold down their finger while they interact with it, and the moment they release, the financial application closes down in order to not expose any information to other people. We can also close applications sooner. So for example, here, Paul is interacting with his emails, being continuously authenticated behind the scenes. When John comes in, the tablet notices that, shuts down Paul's emails, opens John's emails instead, and now he can continue where he left off earlier. And then finally, sometimes we also want to temporarily share access permissions. And we implemented that at the example of the real world scenario, actually, where I hand something over to someone to share it. So what happens here is Paul's trying to access John's gallery, but can't. John, of course, can access it because the gallery has a sense of who's interacting with the photos and the albums. So if he wants to share the permissions with Paul, what he does is he just simultaneously touches the icon, which grants temporary permissions to Paul, and now he can open the gallery. So sometimes you want to support explicit logins, for example, for customized background images or icon arrangements, and we support that too. There's a simple login button, you tap it, and then it logs you in and starts the correct application, but it still authenticates you in the background. So if John comes in now, it would log Paul out. And we can use the same thing to enforce that two people be present in order to access, for instance, the confidential inbox. So it's like turning the keys, right? Two people are here, and then they get this, this very confidential email inbox. So we evaluated two things in our system. First, the bioimpedance. The main point here being we wanted to see if Bioamp is a good platform to sense features that are stable enough to identify people and replicate the results in the related work. 10 participants, I'm going to condense this here. No false positives, and we correctly rejected all the people that were unknown to the system based on the confidence scores we got. And the second evaluation was the transmission rate through the body. So we had the debug interface that was kind of slow, and for comparison, we simulated a touch chip here by gelling an electrode onto the surface and then plugging it into the sound card, which sensed values along the sense line here. We evaluated this in various conditions, with the arm hovering above a table, resting on a table, 3 different materials on the table, and also a sitting pose. Here are the results. This is for the Atmel debug interface. What you can see here, depending on the configuration of the user, basically the grounding or connection to ground, you see how the bit error rate really increases after or at higher frequencies than 12 bits per second. So after that, everything breaks down. With a simulated touch chip, as you can see here, the bit error rate actually jumps from 0 to a value that's slightly above 0 only after 100 hertz. So we get a lot more throughput already, and this is because we get a much higher bit depth. So we sense with 16 bits here. And what's really cool is it inspired us to push this system to the limit. We achieved a 96 kilobyte per second throughput with 18% bit error rate by maximizing the sampling rate and then implementing amplitude shift key. So in conclusion, I talked about biometric touch sensing today, which seamlessly integrates continuous authentication into all interaction, convenient for users and fully transparent, and no sessions, no timeouts, no passwords. We presented various scenarios for input, output, and sharing and context. And the key to making this work and exploring this on today's device is Bioamp, which is a converter of biometric features. So for us, strictly, it's a placeholder technology because we hope in the future tablets will, or all kinds of devices will implement biometric touch sensing themselves without using that extension. But for now, we need it. It's not a token, but it could act as one. And this is the slide I showed you in the beginning, 2-step process, and we think there's a disconnect here. And we think that with biometric touch sensing, we're actually solving that by seamlessly integrating use and authentication. And finally, we think that our concept generalizes beyond the specific wristband that we built or bioimpedance we chose as a feature. So for example, we could do iris recognition and then modulate a signal onto the skin, or embed biometric sensors into mice, keyboards, or even pens that then inform the devices, regular desktops, or even large screens, of who the user is in associating user identities with every touch input event. All right, and with that, I'm happy to take questions.
So we have time for 2 quick questions.
Hey, Christian, Gerard from CMU. Great work as always. So I understand that you did some, because the data rate is limited by the screen frame rate. If you imagine that, let's say the frame rate is infinite, can you characterize the entropy of the bioimpedance? Is there enough entropy in there for authentication?
Yes, there is. And you know, that's, take a look at Corey Cornelius' PhD dissertation. He basically spent his PhD on looking at bioimpedance for identification. He did long-term experiments over the course of like 9 months, I think, and showed how stable the features are, how they decay over time. That's why we picked it. It's a handy platform to integrate that.
So given that, let's say, frame rates could be like 120 or 240, for example, can you push that enough? Like, is there enough entropy to push that into the screen itself?
Oh, I see. Actually, we're describing this in the paper. We're using all the values that we sense when we derive 96 statistical features. So we're reducing the space a lot. And they're good enough to then plug directly into the support vector machine.
That's great.
Okay.
Thanks.
Hi, Gregory Abad from Georgia Tech. Very nice presentation and good work. I noticed in all of your examples, you're using the same finger to interact with the tablet. So I was wondering, when the device is on this hand, if I use different fingers, does it matter? And can I actually use the other hand and do multi-touch?
So the answer is, so there's 2 questions in there. Yeah. So the answer is yes. Actually, I didn't show the video where I used the other hand because it's confusing. But yes, it goes through your body. right? So I can have this device maybe around my ankle, and it still modulates a signal. I can interact using my hands, so that's great. In terms of multi-touch, if there's a single person using the thing, we support full multi-touch, because all of the contexts create this systematic pattern along the sense line. If you have two people, we require them to be on different sense lines. That said, there's a pitch of 4 millimeters between the two, so that's not too bad. We can still tell them apart.
Thanks.
Okay, thank you, Christian.
Right.